Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we were discussing the idea of directional derivative, which involved the idea of gradient also, right? We said that if we have some scalar field in a certain region of space, phi, it was function of x, y, z. So at every point, phi will have a value. This was my space, x, y, and z. So then we said, if we select some point, point be this point, having certain coordinates, x naught, y naught, z naught, and we select some direction defined by some unit vector, u cap, now at this point, along this direction, we want to find the rate of change of phi with distance. That we called directional derivative, and that was denoted by d phi by ds. I repeat, what is d phi by ds? It is rate of change of phi with distance at a given point and it in a given direction. At a given point, for instance, this point P, and in a given direction, for example, in this direction defined by u cap. We said this directional derivative is dot product of two things, this unit vector u cap and del phi. It's called del phi, and it's actually gradient of phi, sometimes written as grad phi. And it is what is I dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. All this thing we have done. Here I name this equation defining my directional derivative as first. So grad phi, gradient of phi is a vector. It has components. This is its x component, dou phi by dou y. Its y component, dou phi by dou z is its z component. So its components are partial derivatives. Now we want to give geometrical interpretation to gradient of phi. Now, when we consider this field phi or any field, we can connect those points having same value of phi. So we get surfaces of constant phi, or we call them contours. I repeat, in the scalar field phi, there may be many points at which phi has same value. If we connect those points having same value of phi, we get a surface. We call those surfaces level surfaces or contours. Keep this in mind. Now let this be some surface along which phi is constant, right? So along the surface phi have a value, but at every point of this surface phi is same. Now let this be my direction of my unit vector, right? And let me use another color. Let this be gradient of phi. This vector be gradient of phi. Now from figure first, not figure first, equation first, this is just a dot product, and you know the definition of dot product. If there is A dot B, that is magnitude of A, magnitude of B into cos of theta, where theta is the angle between A dot A and B, right? Similarly, I can use this definition of dot product here. I can write dou phi, go to the next page. I can write dou phi by, d phi by ds can be written as magnitude of del phi, magnitude of u cap, the cos of the angle between u cap and phi. Let that be this theta, right? Now, since it is a unit vector, its magnitude is 1. So I will have magnitude of gradient of phi and cos theta in the equation, because unit vector, magnitude of unit vector is 1. So see, you can see d phi by ds is actually component of gradient of phi along u cap. See how? If I draw perpendicular from the tip of del phi, let me use another color, then this projection, this length is what? It is d phi by ds in this length, d phi by ds in the direction u cap. Just like in vectors, if you have vector A, vector B, then you have theta, then this length is b cos theta, component of b along A. Likewise, magnitude of gradient of phi cos theta is simply this length, right? This component of gradient of phi in the direction of u cap, and which is equal to d phi by ds in the direction of u cap. So directional derivative in some direction is simply projection of del phi, gradient of phi, or component of gradient of phi in that direction, right? It's one thing. Now if theta changes, directional derivative will change. What is the maximum value of cos theta? Maximum value of cos theta is 1, and that is for theta equal to 0. That means if theta is 0 degree, then u cap coincides with del phi, and this d phi by ds has maximum value, which is equal to del phi, right? So what is the meaning of that? Meaning of that is the largest value of directional derivative is equal to the magnitude of the gradient of phi, and it is in the direction of gradient of phi, because theta, when theta is 0, u cap will be along del phi. So I repeat, the largest value of the directional derivative is equal to the magnitude of the gradient of phi, and it is in the direction of the gradient of phi. Now if we go in opposite direction, if theta is 180 degree, then cos 180 degree is -1, then d phi by ds will have largest negative value, will have largest negative value, and that largest negative value will be minus del phi magnitude of the gradient of phi. So in other words, the largest value of d phi by ds is equal to del phi, and it is in its direction, right? That means largest rate of increase of phi, right, is in the direction of gradient of phi, and the largest rate of decrease of phi is equal to in magnitude del phi, but is opposite to the direction of del phi. This thing you need to remember. I repeat, the largest rate of increase of phi is in the direction of gradient of phi and equal to its magnitude. The largest rate of decrease of phi is opposite to the direction of gradient of phi and in magnitude is equal to the gradient of phi, right? So this is its largest negative value, this is largest positive value. You can write here min also. Then my next thing is I will write some other expressions involving del, some other expressions involving del. Now if we write del phi, that is gradient of phi, as I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z of phi, right? Then this bracket we call del, right? Now by itself, this del has no meaning, right? By itself, I repeat, by itself, it has no meaning. Just as dy dx, it has no meaning by itself when it is alone. Why? We must put some function in front of it here. Some function we have to put here, which is to be differentiated in order to give meaning to d by dx. So d by dx indicates a certain operation, and it operates on the function which is placed in this bracket, right? Likewise, this del, this bracket, this thing is a vector operator. It is a vector operator. By itself, it has no meaning. Only when you put some function here, some field here you have put here phi, it operates on that and we get certain quantity. So we give meaning to this operator. Now suppose v of x, y, z is a vector function, is a vector function. That is, it is three components vx, vy, and vz are functions of x, y, z. That means v is some vector field. That is, v can be written as function of x, y, z. It has components vx, which itself is function of x, y, z. It has y component, which itself is function of x, y, z. It has z component, vz, which itself is function of position. That means v represents a vector field. So v represents a vector field. It can be any vector field. We have explained in last lecture the idea of a field. It can be electric field around some point charge. It can be gravitational field around some mass. So it is in general some vector field. That means at each point of space there is a vector v. The magnitude and direction of v may vary from point to point. Now we can form two useful combinations of del and V. One combination is called divergence, divergence of V, which is written as divergence of V, div, divergence of V, or del dot V. That means divergence of V is what? Just like a dot product. Divergence V is dou by dou x of Vx plus dou by dou y of Vy plus dou by dou z of Vz. So this is the definition of divergence of a vector field. Now you can see divergence of a vector field is itself a scalar. It's just like a dot product. You know, if you write a dot b, you can write it ax bx plus ay by plus az bz. Similarly, dou by dou x is x component of del, vx is x component of v. Dou by dou y is y component of del, vy is y component of v. Dou by dou z is z component of del, vz is z component of v, as we know from the definition of del and v, right? So this operation, this combination of del and v is called divergence. Similarly, we define another operation that's called curl of v, curl of a vector field, right? Now curl of v is written as del cross v, right? We write curl of v, some vector field which is curl v written also, is just like a cross product. We write it in terms of this determinant I cap, j cap, k cap, then I write dou by dou x, dou by dou y, dou by dou z, then vx, vy, vz. Now remember, we write cross product of A and B as I cap, j cap, k cap, then you write ax, ay, az, then you write bx, by, bz. In order to get A cross B vector, we expand this determinant. Similar is here situation. You define curl of V as sort of cross product between del and V. How del is here an operator, A is just a vector. So then you write I cap, j cap, k cap. These partial derivatives are components of del. Vx, vy, vz are components of V. So now curl of vector field is what? A vector. It's a vector. So you need to remember these three operations or quantities. So one is our gradient, This was gradient of phi. It is a vector, right? So when we talk of gradient, we are considering a scalar field. Phi is a scalar field, and gradient of phi itself is a vector field. It becomes a vector. And when we talk of divergence and curl, we are considering a vector field V. Divergence of a vector field itself is a scalar defined by this equation. Curl of V defined by this equation is also a vector, and here is also involvement of a vector field, right? There is another thing, let me do that also. That's called a Laplacian. See, I said divergence. This is divergence. I should write here. Uh, Divergence of V. Divergence of V. Right? This was curl of V. Divergence of V is a scalar. Now, divergence, in case of divergence, we have a vector field. Now, my gradient of scalar is also a vector field. Gradient of some scalar field is also a vector field. That means in divergence, I can replace this V with what? With gradient of phi. Because gradient of phi is itself a vector. So what can I do? I can take the divergence of gradient of phi. I can define divergence of gradient of phi. And I can write divergence of grad phi, and that will be del dot grad phi, right? This thing has a name. This is called Laplacian of phi. Laplacian of phi. It is simply divergence of gradient of phi. Now you can treat it like a dot product. You know components of del. What are components of del? Dou by dou x, dou by dou y, and dou by dou z. You know components of gradient of phi. See, gradient of phi, components of gradient of phi are dou by dou x of phi, dou by dou y of phi, dou by dou z of phi, right? So what will it become? Gradient of phi, I will write it another color, as components dou by dou x of phi, dou by dou y of phi, and dou by dou z of phi. So when you do the dot product, what will it become? Dou by dou x, dou phi by dou x, dou by dou y, dou phi by dou y, dou by dou z, dou phi by dou z. Dou phi by dou y is dou by dou z of dou phi by dou z. It is simply what? It is second order derivative of phi. Second order derivative. It is written as dou 2 phi by dou x2 plus dou 2 phi by dou y2 dou 2 phi by dou z2. This is written as del square phi. So it's easy. Don't be afraid of it. It simply means you have to first find dou phi by dou x. What you get, you differentiate it with respect to x. First you find here dou phi by dou y, then you differentiate that with respect to y partially. There you find dou phi by dou z, then you differentiate that with respect to z partially. So that is the meaning of second order derivative, partial derivative with x. Second order derivative of phi with respect to y, partial derivative. Second order partial derivative of phi with respect to z. So it is called Laplacian of phi, and it is a scalar or vector. It's a scalar, dot product of two vectors, sort of. So it's called Laplacian of phi. It is a scalar, right? Now you know, I summarize these things. So now you know what is the gradient, you know its physical interpretation, geometrical meaning. Gradient of phi is a vector defined by this. Then you have divergence of some vector field. This is the defining equation. It's a scalar. Then we have curl of some vector field defined by this equation. It's a vector. Then we have, what is this? Then we have, missed one page, okay. Then we have a divergence of gradient of phi, right? That's called Laplacian of phi. That's a scalar quantity, right? So you need to remember these quantities. I'll give you or I will discuss another thing. Then I will give you homework. My next topic is in fact triple products. What are triple products? There are two products involving three vectors. One is called triple scalar product. We have two kinds of triple products which involve three vectors. One is called triple scalar product. Triple scalar product because resulting quantity is a scalar. And we have triple vector product because the resultant quantity is a vector. So I will first discuss triple scalar product, right? Let me start on this page. So if I discuss triple scalar product. Now we define this. I take three vectors, so I write it A dot B cross C. So I have three vectors A, B, and C. Now out of those three vectors, I construct this quantity triple scalar product. I take first B and C, cross them. So this bracket is a vector. Then I dot it with vector A. So resulting quantity is obviously a scalar. Now I will show you that this A dot B cross C is geometrically what? Is geometrically the volume of a parallelepiped which we obtain using ABC as three intersecting edges. I repeat, it is geometrically the volume of a parallelepiped. What is parallelepiped? Parallelepiped is solid with six faces. All six faces are parallelograms, right? The cube is also a parallelepiped. So it is a the volume of a parallelepiped which we obtain by using ABC as three intersecting edges of the parallelepiped. I will show it. I will draw a diagram and explain to you. I think I will use next page. So we draw this figure. So I will use another color. Let this be my B vector. This be my C vector. I think I will erase it first. Get my pen back. Okay. So this was my B. This is my C. Right? And this is my A. Let me complete this first. So this is my base. Then what I do, I first complete this. It's always difficult to draw three-dimensional thing on a two-dimensional page, at least for me. Then go to this. Then I will do this. Then do this. and this. I hope the figure is clear to you. See, this is one face of the parallelepiped, lower face. This is the upper face. This is this side face, right? This is another face. This is front face, and this is back face, right? So let this angle be this color. Let this angle be theta. Now what is B cross C? B cross C we know from our previous discussions that B cross C, oh, this is my B vector, this is my C vector, and this is theta. If I find the area of this parallelogram, this area is actually the magnitude of B cross C vector, right? You know this. So this base area, this area of base is what? The magnitude of B cross C vector, right? Now you know B cross C vector is perpendicular to the plane formed by B and C. So B cross C vector is along this direction. Not the right thing. No. This is B cross C. Perpendicular to the plane of B and C, right? Let angle between A and B cross C be phi, right? Got it? Angle between A and B cross C is phi. Now, then what is A cos phi? What is A cos phi? A cos phi is simply what? It is component of this vector along B cross C. That is this. Let me, this length is A cos phi, right? This is area of the base, magnitude of B cross C, right? And A cos phi is the component of A along B cross C. Component of A along B cross C, which is also what? Which is also the height of this parallelepiped. So area of the base into height of the parallelepiped gives me volume. That means volume of the parallelepiped is area of the base, which is B C, magnitude of B, magnitude of C into sine of theta. That is the magnitude of B cross C into the height A cos phi which is simply B cross C magnitude of A into cos phi, which is simply A dot B cross C. Got it? B cross C is the area of the base. Height is A cos phi. So this I write as B cross C magnitude. And I write as A cos phi. Now this is the definition of dot product. A, this vector, into cos of the angle between the vectors, which is phi. So I can write it A dot B cross C. Now since phi can be greater than 90 degree, this phi can be greater than 90 degree, that will make this dot product negative. So it is appropriate then to say that the volume of the parallelepiped is the modulus of this, right? In order to eliminate that negative, in general we say volume of the parallelepiped, which we have shown in the diagram, is mod of E dot B cross C in order to exclude the possibility of negative volume. We cannot have a negative volume, right? Now I can write it this way also, since B cross C is this determinant I, J, K, Bx, By, Bz, and Cx, Cy, Cz. A dot B cross C can be written in component form using this determinant Ax, Bx, sorry, Ay, Az, Bx, By, Bz, Cx, Cy, Cz. So you need to remember this. This completes my triple scalar product, right? So triple scalar product is constructed out of three vectors A, B, and C. Is a scalar that geometrically is the volume of the parallelepiped constructed by or obtained by taking ABC as three intersecting sides as explained in this diagram. And we said since this phi can be negative or phi can be greater than 90 degree, then this dot product can go negative. So it is appropriate to say that volume of the parallelepiped is modulus of this, and in component form you can expand this triple scalar product using this determinant. So I will give you some homework. It's a good question. So homework. Don't miss your homework. Very important. Question first is starting from the point 1 1 in what direction does the function y equal x square minus y square plus 2xy decrease most rapidly, right? This is my question first. Starting from the point 1 1, in what direction does the function phi equal to x square minus y square plus 2xy decrease most rapidly, right? Then my question 2 goes like this. Compute the divergence and curl of each of the following vector fields. Tungsten parts. We use another color. Part A is R equal to xi cap plus yj cap plus zk cap. Part B equal R equal to xi cap plus yj cap. Part C is B equal to zi cap plus yj cap plus xk cap. Then part D, V equal to x square I cap plus y square j cap plus z square e cap. This square here. I repeat the question. Compute the divergence and curl of each of the following vector fields. I'm given 4 vector fields. I have to find their divergence and curl. First is r equal to xi cap plus yj cap plus zk cap. Second is r equal to xi cap plus yj cap. Third is v equal to zi cap plus yj cap plus xk cap. And the fourth one is v equal to x square I cap plus y square j cap plus z square e cap. So this is all for today. Do your homework or listen to these video lectures carefully. You can learn at your own pace. If you find some confusion somewhere, you can pause the video, listen again, right, until you understand. Thank you. God bless you. Assalamu alaikum.